Good evening, everyone. Myself Devika, working as assistant professor in the Department of Electrical and Electronics Engineering at Sri Muthukumaran Institute of Technology. Today we have learned the subject on MR3452 Control Systems Engineering for 2021 regulations. Now I am going to present a brief review of partial fraction expansion, which is an important concept in control systems engineering for the time response analysis. So importance of partial fraction is used in control systems to simplify the transfer functions. So it helps in finding the inverse Laplace transform easily, and it plays a major role in analyzing the time response of systems. Introduction. So the time response of a control system is obtained by taking the inverse Laplace transform of the output, which is the product of input and transfer functions. Since transfer functions are usually complex, partial fraction expansion is used to break them into simpler terms. Then purpose of PFE. So the purpose of the partial fraction expansion converts the complex rational functions into simple functions. So this makes the inverse Laplace transformation straightforward, and it reduces the mathematical difficulty. Then types of transfer functions. So in control system, transfer functions are classified based on the poles into three types: functions with distinct poles, repeated poles, complex conjugate poles. When the transfer function has distinct poles, so when all the poles are different, the transfer function can be expanded into simple fractions. So it making the inverse Laplace transform easy. So in here, let T of s equal to k divided by s into s plus p1, s plus p2. So by partial fraction expansion, T of x can be expressed as, we have to introduce the three variables, three terms in the denominator. So we have introduced the three terms: a by s plus b by s plus p1 plus c by s plus p2. Then we have to find the residues a, b, c are given by. So a is equal to T of s into s. So likewise b and c. So then we have to see the one example of the transfer function as distinction poles. So here T of s equal to 2 divided by s into s plus 1, s plus 2. So we have to find the three variables a, b, c. Then we have to find the residues, and we have to find the partial fractions. Then when the transfer function has repeated poles. So if the transfer function has repeated poles, the expansion contains higher order terms. This case requires careful calculation during the expansions. So T of s equal to k divided by s into s plus p1 into s plus p2 in the whole square. So s plus p2 in the whole square is the repeated terms. So in this case, the T of s, we have to introduce the four variables. So for a divided by s plus b divided by s plus p1 plus c divided by s plus p2 in the whole square, again d divided by s plus p2. So then we have to find the residues a, b, c, d all given. Then case 3, when the transfer function has complex conjugate poles. So for complex conjugate poles, the expansion results in sinusoidal terms in the time response, which is represent oscillatory behavior. So here let T of s equal to k divided by s plus p1 into s square plus s square plus bs plus c. So in numerator term, the characteristic equations are present. So we have to express as T of s equal to a divided by s plus p1 plus for characteristic equation we have to introduce the bs plus c. Then we have to find the residue a, b and c. These are one of the example for multiple complex conjugate poles. So in here example T of s equal to 1 divided by s plus 2 into s square plus s plus 1. So by partial function expansion, T of s equal to, we have introduced the two variables. So a for s plus 2 we have to introduce the a. So a divided by s plus 2. Then for characteristic equation bs plus c divided by s square plus s plus 1. Then we have to find the residues. So a is obtained by multiplying T of s by s plus 2. So a is equal to 1 by 3. To solve b and c, cross multiply the following equation and I substitute the value of a. Then equate the like of power s. So Here 1 is equal to a into cross multiplication, a into s square plus s plus 1 plus bs plus c into s plus 2. So then we have to find b and c. So on equating the coefficient s square terms, we have to find b. On equating the coefficient of s terms, we have to find the c. Then we have to apply the transfer function. So we have to find the time response. Then response of first order system. So for unit step input, the closed loop order system with unity feedback system is shown in figure. So the closed loop transfer function C of s divided by R of s equal to 1 divided by 1 plus st for first order system. So if the input is unit step, then R of t, mathematical representation R of t is equal to 1. So we have to Laplace it R of s equal to 1 by s. So the response in S domain, C of s equal to R of s into 1 divided by 1 plus st. So we have to write it 1 divided by s into 1 divided by 1 plus st. Then we have to by applying partial fraction expansion. So we have here we have two distinct sports. So we have introduced the two variables a and b. Then we have to find the residues of the residues a and b. Then we have to apply the transfer function. So we have to get the time response of the system. So the response in time domain is given by c of t is equal to 1 by 1 minus e power minus t divided by t. This equation is the response of closed loop first order system for unit step input. So for closed loop first order system, unit step response is equal to 1 minus e power minus t divided by t. So for step response is equal to a into 1 minus e power minus t divided by t. So for we have to draw the graph for various of t is equal to 0 to infinity. Then we have to get the c of t, time response of the system. Then response of first order system for unit ramp input. So for unit ramp input, the mathematical representation R of t is equal to t. So we have to Laplace it, we R of s divided equal to 1 by s square. So output response C of s equal to R of s into 1 divided by 1 plus st. So we have to substitute R of s instead 1 by s square instead of R of s. So we have to get the C of s equal to 1 by t divided by s square into s plus 1 by t. Then taking partial fraction expansion, we have to introduce the three variables. Then we have to find the residues a, b, c. Then we have to get the c of s equal to c of s equal to t into 1 minus e power minus t divided by t. Then we have to apply the t for t is equal to 0 to infinity. Then we have to get the time response in time domain. Then for unit impulse input, for impulse function, R of t, mathematical representation R of t is equal to del of t. So R of is equal to 1. Then we have to substitute it and we have to find the residues A, and we have to get the output response in time domain. Then advantages of first order systems. First order systems are simple to model and it is easy to analyze and provide stable responses without the oscillations. So they require fewer components and have low computational complexity. Applications of first order systems. So first order systems are used in RC and RL circuits and temperature control systems, liquid level control, speed control of DC motors and thermal systems. Thank you. This brings me to the end of my presentation. Thank you for your patience and attention.